Good afternoon, students. Welcome to DBS Talks. Now in this class, we are discussing the subject is utilization of electrical energy. Okay, so in utilization of electrical energy, present we are discussing the fourth unit. Our fourth unit is electric traction 2. Okay, so in this unit, today we are discussing about the power output from driving axles. Okay, so in a previous class, we are discussing about the tractive effect. Okay, so now in this class we have to discussing the power output from the driving axis. That means, so in previous class we are discussing about the tractive effect of the driving wheels. Okay, same that how much power you will get from driving axle. Here we have to discuss. Okay, see here. Let Ft is the tractive effect in newtons and V is the speed of the train in kilometer per hour. Okay, so here you have to assume Ft is the tractive effort and V is the speed of the train in kilometer per hour. So at that time the power output P equal to rate of work done. Okay, so at that so here so work done, work is nothing but distance by time. Okay, so at that time here you have to write tractive effect into distance by time. Okay, so that is nothing but distance by time is denoted as a speed. Okay, so here the power output is tractive effect into distance by time. Okay, here distance by time again you have to written as speed. Okay, so at that time here you have to write. Okay, so the tractive effect is nothing but Ft. Okay, speed is denoted with here V. Okay, so here you have to write in watts. So at that time this is in you have to write newtons. Okay, so and this is in seconds. So at that time here you have to write Ft into V by 3600 kilowatts. If V is in meters per second, if suppose you have to take velocity. Okay, so velocity is in meters per second, then P power value. Power P equal to Ft into V watts. Okay, so if suppose here eta, if the eta is the efficiency of the gate transmission, the power output of the motors. Okay, so at the time the power output of the motors is given by P equal to FTV by eta watts. Okay, so similarly here we have to write in kilowatts. So at the time here you have to represent FTV divided by 3600 eta kilowatts. So that is the power output from driving axle. So next here you have to write the specific energy consumption. The energy input to the motors. Okay, so what is the energy is given to the motors for working is called the energy consumption. Okay, so this is the energy consumed by the various parts of the train for its propulsion. Okay, so to move that train, okay, so to move that train, so here the energy, okay, here the energy will be consumed by the various parts of the train for its propulsion. The energy drawn from the distribution system should be equals to the energy consumed by the various parts of the train. Okay, so what is the energy? So the energy drawn from the distribution system. Okay, what is the energy drawn from the distribution system should be equals to the energy consumed. So what is the energy will be consumed by the various parts of the train and the quantity of the energy and that means so various parts means that is required for lighting, heating, control and braking. So the main workings done in the traction is lighting, heating, control and braking. Okay, so that is for this all purpose here you have it requires the energy. Okay, this quantity of energy consumed by the various parts of the train per ton per kilometer. Okay, so the quantity of energy consumed by the various parts of the train per ton per kilometer. Per ton per kilometer is known as the specific energy consumption and it is expressed in watt hour per ton per kilometer. Okay, and here the specific energy consumption is expressed in the watt hours per ton per kilometers. Okay, see here specific energy consumption is equal to total energy consumption in watt hours divided by the weight of the train in tons into distance covered by the train in kilometers. Okay, so the specific energy and energy consumption is defined as the total energy consumed by the per ton of the train. Okay, so here see this is the specific energy consumption. Total energy consumption in watt hours by the weight of the train in tons into the distance covered by the train in kilometers. Okay, so next here you have to determination of specific energy output from simplified time curve. So in previous we have to discussing the simplified team curves, simplified speed time curves. Those are trapezoidal speed time curves and quadrilateral speed time curves. Okay, so from that, okay, general you have from that simplified speed time curves. So here you have to find out the specific energy output. See here, energy output is the energy required for the propulsion of a train or vehicle is the mainly for accelerating the rest to velocity v. Okay, so energy output. Okay, energy output is the energy required for the propulsion of a train. Okay, so that means for the movement of the train or vehicle is mainly for accelerating the rest to velocity. That means from the starting to some velocity v. Okay, so some energy will be required. Okay, to move from that. So at that time, it's some energy output here you can get. Okay, which is the energy required to overcome the gradient and the track resistance to motion. Okay, so at that time, so this is the energy. Okay, so which is the energy required to overcome the gradient and track resistance to the motion. So energy required for accelerating the train from rest to its crest speed is Vm. So here you can assume the energy. Okay, so the energy which is required for the accelerating the train. Okay, from rest to its crest speed. Crest speed Vm. Okay. So here see the energy required for accelerating the time. So energy is nothing but power into time. Power is nothing but work done by time. So time. So here work done. So work done by time. So here you have to write work done is nothing but tractive effect into velocity into time. So here the tractive effect is given by Ft and velocity. Okay, velocity here you have to written as Vm by 3600 and time period is T1. So at the time it is expressed in here force is in newtons and here velocity in kilometers per hour and time period in seconds. Okay, so at that time here you have to write Ft into 1 by 2 into Vm by 3200 into T1 by 3600. Okay, sorry, here 3600. Okay, so Newton kilometers or kilowatt hour. Okay, so that means here you have to convert the hours total. Okay, total time period into the hours. So at that time it will becomes 1 by 2 Vm by 3600 whole square alpha Ft kilowatt hours. But here T1 from the simplified speed time curve we can assume T1 is the time required to accelerate the train. That means time period and acceleration that is denoted with T1. So T1 equal to Vm by alpha. So at that time in the place of here Vm square by alpha. So at that time whenever you have to so that's why here T1 in the place of T1 here you have to write Vm. So at that time Vm into Vm will becomes Vm square by alpha. So but in previous class we are find out the tractive effect Ft. So tractive effort for the propulsion of train you can get the formula is 277.8 W alpha plus 98.1 Wg plus Wr. Okay, so now you have to substitute this formula in the place of Ft. So whenever you have to substitute here, so at the time this equation becomes like this. So next, so this is the energy required for the accelerating the train. That means specific energy. Okay, see here. That means energy. This is the energy required for the acceleration. So next you have to overcome the gradient, gravitation. Okay, so and see here. Energy required for overcoming the gradient and track resistance to the motion. So next we have to find out the energy required. Okay, energy. So here three forces acting on the train. Those are accelerating force. Okay, gradient force. Okay, the force which is used to overcome the track resistance. Okay, so first here you have to find out the energy required for accelerating the train. Okay, so next here we have to find out the energy required for overcoming the gradient and track resistance to the motion. So here see, energy required for overcome the gradient and track resistance. Okay, see here, tractive effect into velocity into time. Okay, so tractive effect here you have denoted with Ft dash. Okay, Vm by 3600 into time period T2 by 3600. Here gradient. So here I have to mention only gradient and track resistance. At that time there is no energy required for the accelerating period. Okay, so that's why here only you have to write the energy tractive effect for track resistance as well as for gravity. Okay, so at the time this formula will becomes Vm by T2 3600 whole square in the place of Ft dash. Here you have to write Wr plus 98.1 Wg kilowatt hours. See here where Ft dash, see here where Ft dash is the tractive effect required to overcome the gradient and track resistance. Okay, so it is the tractive effect to required to overcome the gradient and track resistance. W is the dead weight of the train, and R is the track resistance, and G is the percentage gradient. So here now you have to write the total energy output. Okay, so whenever you have to find out the total energy output, from that you have to find out the specific energy output. Okay, so what is the formula for specific energy output? Energy output in watt hours to the weight of the train in tons into distance distance of running. So to find out the specific energy output, here you have to find out the total energy output. So the total energy output is equal to energy required for acceleration plus energy required to overcome gradient and to resistance to motion. So what are the formulas you have to find out? Energy required for acceleration is Vm square by 2 into 3600 whole square alpha into 277.8 We alpha plus 98.1 Wg plus Wr. Similarly, energy required to overcome the gradient and resistance to motion is Vm T2 by 3600 whole square Wr plus 98.1 Wg kilowatt hours. So from these all terms, here you have to common 277.8 We alpha. Okay, so you have to write. So in these two terms, you have to 98.1 Wg plus Wr. Whenever you have to common in these two terms, this event separately so this term is only separately written. So similarly, so whenever you have to common from these two terms, Vm square 1000 by 2 alpha 3000 whole square into Vm T2 into 1000 by 3600 whole square. So at that time, this equation, whenever you have to simplify this one, this will become 0.01072 Vm square. Okay, similarly here in these two terms, here you have to 1000 by 3600. Okay, we have to common this term. So Vm by 2 alpha 3600 plus Vm by T2 3600. Okay, so here this is the D1. Okay, and this is the D2. Okay, from the simplified speed time curves, this will become D1 and this will become D2. Here you have to assume. So finally, the specific energy output means energy output in watt hours by weight of the train into distance of running. So in the place of energy output in watt hours, here you have to substitute. Weight of the train is nothing but W. Okay, so at that time, here you have to write distance is D. So divided by W into D. So at that time, here you have to written as, you have to split for these three terms. Okay, at that time, here you have to write D1 plus D2 by D dash, you have to written as D dash. Okay, so at that time D dash will becomes D1 plus D2. So at that time D dash by, so at that time the for uniform level track, so whenever the track is uniform, okay, so whenever the level track is in uniform, at that time G value, gradient, at that time the gradient value will become 0. So whenever gradient will be 0, at that time this term will be 0. Okay, G value will be 0. So at that time here only you have R by D into 0.788 D dash. So at that time this will become the specific energy consumption, energy output by efficiency in of motor. So at that time it will become 0.001072 Vm square by eta D W by W plus 0.2778 R by eta D dash by D watt hours per ton per kilometers. Okay, so this is the specific energy consumption of the train. Okay. So next we have to see the factors affecting the specific consumption of specific energy consumption. Okay, so now you have to see the what are the factors. Okay, so what are the factors will affect the specific energy consumption means first one is distance between the stations. Okay, so the distance between the two stations. Okay, next one acceleration and retardation, and next one maximum speed, and next one is gradient and train resistance. First one is what? Distance. So first parameter, so which is affecting the specific energy consumption is distance between the stations. Okay, see here, whenever you have to see distance between the stations, see from the equation of specific energy conversion, it is inversely proportional to the distance between the stations. So that means whenever the distance between the stations will be increases, so at that time the specific energy consumption value will be decreases. Okay, see here, greater the distance between the stops is, the lesser will be the specific energy consumption. So at that time the specific energy consumption value will be less. Okay, so the typical values of specific energy consumption is less for main services. Okay, so why it is less for mainline services means, mainline services means the distance between the stops is the distance between the stops is more. Okay, whenever the distance between the stops will be more, at that time the specific energy consumption value will be less. So at that time for the mainline services, the specific energy consumption value will be 20 to 30 watt hours per 10 kilometers, and high for urban and suburban services. So why its value will be high for urban and suburban services means, so here the specific energy consumption is inversely proportional to the distance. Here for urban and suburban services, the distance is very less than 1 kilometer, 2 kilometers like this. So whenever the distance will be less, so at that time the specific energy consumption value will be high. So that is 50 to 60 watt hour per ton per kilometers. So next one is what? Acceleration and retardation. Okay, see here, for a given schedule speed, the specific energy consumption will accordingly less for more acceleration and retardation. Whenever acceleration and retardation will be more, so at that time the specific energy consumption value will be very less. Next we have to see the maximum speed. For a given distance between the stops, for specific energy consumption increases with the increase of the speed of the train. Whenever the speed of the train will be increases, so at that time the specific energy consumption of the train will be also increases. So next one is what? Last one, gradient and train resistance. So next we have to see the gradient and train resistance. See here, from the specific energy consumption, it is clear that both gradient and train resistance are proportional to the specific energy consumption. Okay, these two, gradient and train resistance, are proportional to the specific energy consumption. Normally, the coefficient of addition will be affected by the running of the train. So at the condition of the track. So for the wet and greasy track conditions. Okay, so the value of coefficient of addition is much higher compared to the dry and sandy conditions. So whenever the track will be greasy, so at that time coefficient of addition is higher when compared to the dry and sandy conditions. Okay, so that's why the specific energy consumption is proportional to the gradient and train resistance. Okay, so these are the factors will affect the specific energy consumption. So next you have to see some of the important definitions in this unit are, first one is dead weight. So what is the dead weight is nothing but it is the total weight of the train to be propelled by the locomotive. So dead weight is nothing but it is the total weight of the train propelled by the locomotive. It is denoted by W. Okay, so the total weight of the train is nothing but the locomotive is specified as the dead weight. Next one is what? Accelerating weight. Okay, so accelerating weight is nothing but it is the effective weight of the train that has angular acceleration due to rotational inertia, including the dead weight of the train. Okay, so dead weight means only stationary parts weight, but accelerating weight means it having the rotating parts. Okay, that means angular acceleration due to rotational inertia, including the dead weight of the train. Okay, so it is denoted by WE. Okay, so here the accelerating weight is denoted by WE. So the effective train is also known as accelerating weight. So effective weight of the train will be more than the dead weight. Here the effective weight of the, so accelerating weight is also called as effective weight. So the effective weight of the train will be more than the dead weight. Normally it is taken as 5 to 10% of more than the dead weight. So normally the accelerating weight will be taken as more than 5 to 10% more than the dead weight. So next definition is adhesive weight. So what is the adhesive weight? The total weight to be carried out on the driving wheels of a locomotive is known as adhesive weight. So whenever the train is in running position, okay, so whenever the train is in running position, so at that time the total weight Okay, so at that time the total weight to be carried out on the track of the wheels, so that is of a locomotive, that is nothing but the adhesive weight. Next one, final one is what? Coefficient of adhesion. It is defined as the ratio of tractive effort required to propel the wheel of a locomotive to its adhesive weight. So coefficient of adhesion is nothing but it is the ratio of tractive effort, Ft, tractive effort to the adhesive weight. Okay, so at that time it is Ft is directly proportional to W, Ft equal to mu W. Here mu is nothing but coefficient of addition. So at that time here you have to write mu equal to Ft by W. You have to write. Okay, so where Ft is the tractive effort and W is the adhesive weight. Okay, from this formula here formula is missing. So here from this mu equal to, here you have to write Ft by W. That is nothing but the coefficient of addition. Okay, so these are the important definitions in the electric traction too. So now here you have to see one problem on this tractive effort. See here, a 250-ton motor coach having 4 motors each developing 6000 Newton meters torque. Okay, so if suppose a 250 ton, okay, so the weight of the train 250 ton weight of the train having 4 motors each developing 6000 Newton meters torque. Okay, during acceleration starts from rest. Okay, whenever it starts from rest, so acceleration period, it develops the torque value will be 6000 Newton meters. If the gradient is 40 in 1000, that means the gradient value is 40 in 1000. Gear ratio is 4. Gear transmission efficiency, eta value will be 87%. Wheel radius R equal to 40 centimeters. Train resistance R equal to 50 Newton per ton, and the additional rotational inertia will be 12%. So calculate the time taken to attain the speed of 50 km per hour. So here in this problem, here you have to calculate the time period. So to attain the speed of the train will be 50 kilometers. From the starting position to attain the train for 50 kilometers, how much time period will be taken? So that value in this problem you have to find out. So if the line voltage is 3000 volts, okay, so here the line voltage is 3000 volts DC and the efficiency of the motor is 85%. Find the current during notching period. Okay, so here you have to, notching period is nothing but free running period. Okay, first what is the given data? So here you have to note down the given data. So here the weight of the train W equal to 250 tons, percentage gradient G equal to 40 in 1000. So at that time you have to write 40 by 1000 into 100. That time percentage gradient is 4%. Gear ratio R equal to 4. Okay, wheel diameter D equal to so here you have to, in the problem only radius will be given, but the diameter you have to find out 2R. So at that time 2 into 40 centimeters, that will become 80 centimeters. So the centimeters will be converted into the meters. So at that time you have to divide it with 100. So at that time it will become 0.8 meters. And here the train resistance R will be given by 50 Newton per ton. And here the rotational inertia will be given by 12%. So here you have to find out the time period. Okay, so time period. So what is the formula to find out the time period? T equal to Vm by alpha. T equal to Vm by alpha. So that's why here we have to find out the alpha value, Vm value. How you can find out the Vm value? So Vm value is 50. Okay, Vm value is already problem it is given as 50. Okay, so here we have to find out the alpha value. So see here, accelerating weight of the train W equal to, how you can find out the accelerating weight means, so to get the accelerating weight you have to multiplying with dead weight into 1.10. So at that time it will becomes 275 tons. Okay, the torque developed T equal to total torque 4 into 6000. Okay, so why? Because here you are using the 4 motors. So at that time it will become the 24,000 Newton meters. So at that time the tractive effort Ft equal to eta value will be eta in the problem 87%, that means 0.87 into torque 24,000 into 2 into R value, gear ratio will be 4 and D value diameter will be 0.8. So at that time the tractive effort will get 2,08,800 newtons. Okay, but FT equal to what is the formula? 277.8 WE alpha plus 98.1 Wg plus Wr. So from this formula you have to know Ft value, We value, double value, G value, Wr value. But here from this one you have to find out the alpha. So at that time here you have to substitute all these values. So what is the Ft value here in the problem? You have to get 2,08,800, W value 275, alpha plus 98.1, W value will be 250, G value will be 4, W value will be 250, track resistance R value will be 50. By solving this equation, you can get alpha acceleration value, you can get the 1.285 kilometer per hour per second. So here the time taken for the train to attain the speed of 50 kilometers. In this problem here you have to find out the time taken to attain the train of the speed is 50 kilometers per hour. So at the time here you have to write T equal to Vm by alpha. Vm value will be 50. Alpha value will be 1.285 kilometer per hour second. By solving this equation, finally you can get the time period. T equal to 38.89 seconds. Okay, so this is the time period will be taken for the attain the maximum speed of 50 kilometers per hour. See here, to get the accelerating weight of the train. So accelerating weight means dead weight into rotational inertia. So at that time here 1.12. Okay, so at that time 12% means 1.12 into 250. At that time the total weight of the train here you can get the 275 tons. So finally last here we have to find out the power output. Okay, in this problem you have also find the current during the notching period. So current value will be fine. So to find out the current value, so here you have to know the V value and power value. So whenever you have to know the power value, so at that time you have to find out current run by the each motor. So that's why what is the formula to find out the power output from the driving axis? Ft Vm by 3600. So at that time 2,08,800 into Vm value will be 50 by 3600. So at that time here you can get 2,900 kilowatts. What is the efficiency formula? Efficiency equal to power output by power input. So from this efficiency value in the problem, efficiency value will be given 85%. So at that time here you have to write 0.85. So from this power input equal to power output by eta. So to power output 2,900 by 0.85. So at that time power input you can get 3,411.76 kilowatts. So at that time total current run is power input by V. Okay, so here if the line voltage is 3000 volts, so here given if the line voltage is 3000 volts and efficiency is 85%, find the current during notching period. So at that time voltage value will be given. So that's why here in the place of efficiency here you have to write 0.85. Okay, so power input value you can get 3411.76 into 10 cube divided by V. Okay, so voltage value, line voltage DC, here the line voltage is DC and it is given by 3000. So at that time it will be that total current value you can get, okay, so 1137.25 amperes. Okay, this is the current run by the 4 motors. So here it is measured with 4 motors. So at the time current run by each motor you can get. So at the time this 1137.25 is divided with 4. Okay, so whenever you have to divide, so 1137.25 divided by 4. So at the time you can get 284.31 amperes. Okay, so this is the current run by the each motor. That is whenever it whenever you have to given the voltage, power voltage value is 3000 volts. So at the time the current run by each motor you can get the 284.31 amps. Okay, so here you can understand. So here why you can, so here mistake not 1.10, here 1.12. Why? Because here rotational inertia will be given by 12%. Okay, so that's why here you have to write 1.10 into 250. That is equal to finally here you can get 275 tons. Okay, so this is the solution for this problem. Okay, so now in this class we are discussing the power output drawn from the driving axis, specific energy consumption, and what are the factors. Okay, so the main factors which are affecting the specific energy consumption, and finally we have to discussing some of the important definitions. Those are adhesive weight, dead weight, accelerating weight, and coefficient of adhesion, and you have to see the problem. Okay, thank you.